Hello there and welcome to A-Level Further Maths. Here we're looking at the second part of first order differential equations so we can answer questions from exercise 7a. In the previous video we saw how to solve first order differential equations by separating the variable. In this video we're going to have a look at how we would use the reverse of implicit differentiation to solve first order differential equations. Let's have a look at the first question up here. Find the general solution to the following equation. X cubed dy by dx plus 3x squared y equals sine x. Okay, well what you might be able to identify, in this example you would not be able to separate the variables easily, if at all. You can use the pattern from the product rule, however. The product rule is this rule here, where you've got u, if you're differentiating u times v, the answer is u times the differential of the v, and then plus the other way around, v times the differential of the u. And we can kind of see that pattern in the left-hand side of what we've got in our equation. If we were, imagine we were finding the differential of x cubed y by doing some implicit differentiation. So we're going to set u equal to x cubed and v equal to y. In the product rule above, we would differentiate the x cubed first to 3x squared, and then in the second part we'd have to differentiate y, and y differentiated with respect to x is dy by dx. So when we use the product rule and when we use implicit differentiation, we get this expression here, which is exactly the expression we've got on the left-hand side. So what we could say here is that the left-hand side of the equation we're about to solve is the differential of x cubed y. So notice that the differential of x cubed y is equivalent to the left-hand side of the original equation. This means we can replace it, they're equivalent. So we'll replace the left-hand side now with the differential of x cubed y. And now we can go ahead and solve this as a differential equation. Now we know that the derivative of x cubed y with respect to x is sine, let's just undo that derivative. What we'll do now is we'll take integrals from both sides, and you can see here effectively what will happen is, because this is a derivative that's being integrated, the two things will effectively cancel each other out. So we'll just be left with, on the left hand side, x cubed y. And on the right hand side we'll have to integrate sine. That will be minus cos plus c. So you can see here how once we've worked out that the left hand side was a derivative of x cubed y, when we integrated the derivative, those two things cancel each other out, they're opposites, so it's x cubed y. And then on the other side you integrate the right hand side, that would be minus cos x plus c. We might want to divide by x cubed if we want to just make the equation with y as the subject. Other forms of the answer, such as the one above, are also fine. So something like that. Okay, so you can use a general pattern to see whether this is doable. It is possible if the conditions to the right are met. The general pattern that we've got to follow is that we've got a function of x, and then its derivative on the other portion of the expression on the left hand side, and then a y, and then a dy by dx. So as long as you've got, it's really the key part is, you've got something that's being multiplied by dy by dx, and then its derivative must be multiplied by y, and then the two things must be added in the middle. It doesn't really matter what's on the right hand side at this point, as long as we've got this kind of structure here, where we've got a function and its derivative, one multiplied by dy by dx, one multiplied by y, that will perfectly follow the pattern of implicit differentiation, where the left-hand expression is being multiplied by y. Okay, so can we now generalise this? Can we generalise this to solve an equation like dy by dx plus py equals q? So anything that was in front of dy by dx to start with is just divided through by that function. Okay, what we're looking to do is we're looking to turn it into something like this, where it's the function f of x times dy by dx plus, and then the differential of that f of x times y, because what we can then do is we can then simplify that to the derivative of f of x y. and then we can just undo the differential by integrating both sides. So what we'll do then is we'll start with, so just one thing to highlight here, P and Q. P and Q are not just numbers here, they are functions of x. So they could be something like tan or sine or e to the power of x or ln of x, something to do with x in there. Okay, let's have a look at what we've got then. dy by dx plus py equals q. P and q are functions of x. So what we need to do then is multiply by that f of x, because f of x appears at the start of the dy by dx, and then what we need to make sure happens is that, so f of x has been multiplied to the start of everything. That blue that came up there just really highlights that f of x is multiplied by everything. And now, since we know that this thing will become a derivative of f of xy, that only applies if the f of x times p, so if we look at the second terms here, we're just looking at these terms here, we're looking for f of x py to equal f dash of xy, because the first terms nicely match up. You can see it's the second terms we now need to match up. So what we now need to do is divide through by that y, and we're looking for this condition to be satisfied. F of x times p equals the derivative of f of x. Now how could we work out what f of x is? But let's divide through by f of x, and then with p equals f dash of x over f of x. The next thing to do is to integrate both sides. We're looking to work out what f of x is. The integral of the right hand side is ln f of x, and then to get rid of the ln we just need to e both sides. So we've got e to the integral of p dx equals our f of x function. This is our integrating factor. That's what this is called, integrating factor. So yeah, it's just e to the integral of p dx. And it looks like something that would be quite complicated, but we'll see plenty of examples where this is quite easy to work out. So that's our function f of x. So what you'll do in most questions is you'll take your differential equation, such as this one here. You'll then work out what your integrating factor is, and then multiply your integrating factor the whole way through. The reason you've done this is so that the f of x times p function will simplify to f dash of x. That's how we've set up this f of x function, so that definitely does happen. Then you use reverse implicit differentiation, and that would be the derivative of f of xy equals f of xq, and then integrate both sides with respect to x. That will cancel out the derivative, so integrating will cancel out the derivative, and on the left hand side we'll get f of xy equals the integral of f of x times q dx, and your final thing to do to work out a solution to the first order differential equation will be to integrate the right hand side. So inside these questions there's two things that you need to do. There's two integrals you need to work out. You first need to work out your integrating factor integral, and then you need to work out your integral for f of xq on the right hand side. So let's see this in action then. So just to highlight up at the top, first you work out your integrating factor, then your solution is going to be this expression here, f of xy equals the integral of f of xq dx. That's always going to happen. It's always going to be the case that that happens. So we can follow that structure for most questions. For question 1, the first thing we need to do is work out what the integrating factor is. So p here is going to be the coefficient of y. It's always the coefficient of y, so it's -4. So the integrating factor is going to be f of x, whoops, another bracket there, f of x equals e to the integral of p dx. P is the value -4, so we'll integrate -4 to -4x, and e to the -4x is going to be the integrating factor. So the next thing to do is work out the solution. So what we then do with that e to the -4x is multiply it on the left hand side where the y is. What we're effectively doing now is setting up this right hand thing at the top of your page here. So it's going to be e to the -4xy, that's f of x times y, will equal the integral of e to the -4x, that's your f of x again, times e to the x, because that's q on the right hand side. So you can see where each of these individual components has come from. The first one is f of x, the second one is y, that's just y, it's always going to be just y, equals the integral of the f of x function times q, which is your answer on your derivative. Simplify what you've got there, then integrate it, and then that's your final answer. And you may want to times by e to the 4x all the way through. So there we are, that's the answer to this question. So it comes in two parts. You can clearly see, do your integrating factor first, then work out your solution second. Let's have a look at the second one then. So this time it's 3x dy by dx plus c equals x. First thing to do will be to divide by the 3x to get dy by dx on its own at the front. The next thing we need to do is identify what p is. Therefore p is 1 over 3x. It's the coefficient of y every time. So then when we do the integrating factor, it's going to be f of x equals e to the integral of p dx. So it's going to be integral of 1 over 3 dx, which is going to be the e to the third ln x, and then we simplify this, we move the third inside the ln as a power, and then cancel out the e in the ln. So the integrating factor here is going to be x to the power of a third. Now that we've done the integrating factor, we now go for the solution. So the solution is going to be of this form here. F of xy equals the integral of f of xq dx. It's always this. So f of x is x to the power of a third, y, and then that would be equal to the integral of f of x, that would be x to the power of a third, times q, and q is highlighted by this thing here. It's the answer on the other side of the derivative, once you've simplified to make it dy by dx on its own. So that's why the third has come in here. Let's now integrate the right hand side. It's going to be 1/4 x to the power of 4 over 3. And then we might want to divide by x to the power of a third. That will leave us with 1/4 x plus c x to the minus a third. So don't forget to put the plus c when you're working out your solution. And there we are, that's the answer to part 2. And moving on to the third question, it's going to be divide by cos first, and then we'll get this expression here. Therefore p is going to equal 2 tan x. So now we can start working on the integrating factor. It's going to be e to the integral of 2 tan x. Let's now integrate the 2 tan x to 2 ln sec x. Let's now put the 2 inside the ln and cancel out the e in the ln. So then that will be sec squared. Now that we've worked out what the integrating factor is, time to go on to the solution. So it's going to be of this form here. This form is always the solution. It's going to be sec squared y equals the integral of sec squared x cos cubed x. That's q from the right hand side of your derivative equation. Simplify what you've got there and then integrate. So sec squared will cancel out 2 of the coses. Integral of cos is sine. And then we may want to multiply by cos squared on both sides to leave us just with y on the left. So it's going to be sine x plus c times cos squared x. Lovely, there we are. That's how we work out these first order differential equations. First of all, you work out the integrating factor, and it's always e to the integral of p dx. And then you work out the solution, and it's always of the form f of x, y equals the integral of f of x q dx. This is f of x I've just defined above here. That's the integrating factor. Okay, so there we are. So what I'd like you to do now is just take a pause on the video and have a go at this question that's appeared now. So pause the video, give this question a go. Okay, so the first thing to do to start with is first work out the integrating factor. This is going to be e to the integral of cot dx. Now the integral of cot will probably be in the formula booklet, but if it isn't, it's just going to be cos over sine. That looks like a ln derivative to me. The ln of the bottom equals the top, so it's going to be e to the ln sine x, which will simplify to sine x once you cancel out the ln. Okay, moving on to the next thing, we're now looking for the solution. It's going to be sine x y equals the integral of sine x times by 1 dx. So it's going to be sine x y equals minus cos x plus c. And I may want to divide by sine on both sides, and that will be effectively the same as multiplying by cosec. So it'll be cosec x bracket c minus cos x. And there we are, that's the answer to this question here. So it's as easy as going integrating factor here, solution here. Lovely, thanks very much for watching that video. Hopefully you found it helpful. Please now have a go at some questions from exercise 7a, page 151. I think these questions start from question 7 and carry on onwards. The previous video contains the method to do the previous set of questions with, so 1 to 6. So carry on from question 7 from this video on page 151. Thanks for watching.